Do you ask yourself why some systems keep oscillating while others stop oscillating after a certain time? In this video, I will give you a short introduction to free and forced vibrations. We will discuss the differences, which systems are realistic under which conditions, and under what circumstances a vibration is considered free or forced. Let us consider a vehicle suspension that can perform a more or less vertical motion in the Z direction and is supported by a spring damper system. This system can, for example, be excited by an uneven road surface where an external force, namely the road's tire force, acts vertically on the tire. Another everyday example is a washing machine. Due to the high rotational speeds of the drum and an imbalance of the laundry, a centrifugal force acts outwards. This results in a vertically oscillating force and therefore causes the washing machine to undergo a time-dependent vertical oscillation as long as the eccentric force from the drum imbalance is present. In general, we can simplify the system shown as a linear, single degree of freedom oscillator with the mass m, spring stiffness k, and viscous damping coefficient d. The system has 1 degree of freedom z, and the general equation of motion is mz double dots plus dz dots plus kz is equal to the external force. In the case of free vibration, there is no external force applied. The system is not excited from the outside, therefore F external is equal to 0. Instead, the system can be set into motion by initial conditions. For example, it can be displaced by an initial displacement Z0. This is called an initial condition. The two possible initial conditions are initial displacement Z at t0 or initial velocity z dot at t0. Initial conditions introduce energy in the system. Therefore, the system performs a free vibration and processes the introduced potential energy through Z0 or the introduced kinetic energy through Z dot 0. Here you can see the response of the system due to an initial displacement of 1 cm. In the suspension example, this would correspond to driving over a small road bump, which sets the system into its natural oscillation. There is no external force acting. Only the initially introduced potential energy due to the displacement causes the system to release and redistribute the energy stored in the spring. As we can see, the result is a damped oscillation that decays over time. The damper causes energy dissipation, which means that the energy initially introduced into the system is converted into heat inside the damper, then is removed from the mechanical motion. In the graph, according to the period length, one can see that the system oscillates with its natural frequency. How to determine this natural frequency from the equation of motion is explained in a separate video, which you can find in the end screen. This means that only the system properties determine the oscillation periods. Now let us consider forced vibration. In this case, we remove the initial conditions and instead apply the harmonic excitation force. F external is equal to F hat times the sine of omega t. Energy is now continuously supplied from an external source, and the system oscillates with exactly the excitation frequency, not in its natural frequency anymore. In this case, the oscillation does not decay as long as energy is continuously supplied from the outside. In contrast to free vibration, the externally supplied energy is now converted into heat in the damper during steady operation. If we look at the force signal shown in red, and below the vertical system response shown in white, we can observe the following properties of forced vibration. The oscillation response has the same period and therefore the same frequency as the input signal, which is the harmonic force input. The response follows the force signal with a small delay, delta phi. This is called the phase lag of the response. In the lower graph, we see that after a certain time the system reaches the so-called steady state, where the amplitudes oscillate harmonically between two limits. The region on the left represents the transient response, where the system starts from rest and needs some time to reach steady-state oscillation. Finally, here is a short overview of the main differences between free and forced vibration. An external force occurs only in the forced vibration. The energy input in the free vibration comes solely via the initial conditions, whereas in the forced vibration, there is a continuous external input. The free vibration oscillates in its natural frequency, but the forced vibration in the excitation frequency from the external source. And assuming damping is considered, which is always the case in real systems, the free vibration decays after a certain time, whereas the forced vibration maintains its oscillation as long as the external source delivers input energy. Make sure you subscribe to not miss the upcoming videos, where I will cover forced vibration, resonance, and other interesting dynamics fundamentals in detail.